Okay, so let's continue with variable reconstruction. So now each of the variable has to be reconstructed, and whoa, this full page looks like full of errors. Oh my god. Okay, so let's take one step at a time. Let me get rid of all of this, that is, comment it out, and now I have to deal with only these 4 things. So okay, now cell ij. Now instead of using ij again and again, let me say cell is equal to cell ij. Oh sorry, cells ij, and let me call this cell or you can name it, say, this cell or something like that, just to say that it's particular cell that you are referring to. Okay, so this is fine. Now we are going to have to set up each of the variables, and it's very easy. You just have to, for each of the variables, number of variables, I just have to copy paste it right inside here, and now u west is going to be equal to each of the variable. So each of the variable is going to be equal to the variable value inside the cell. So I think I can just copy paste this particular thing 4 times, 2, 3 and 4. Okay, so now this thing is done, and our variable reconstructor, at least the first order thing, is complete. So let's go to Flux now, and this is, I think, the most important thing. Yeah, first of all, total flux has to be initialized to 0 for each of the variable. Because we are going to add the total flux every time, so that's going to be equal to 0. And okay, as of now that's fine. Okay, now I have to think a little bit. Yeah, it's fine if I just copy the value, because I'm not going to change the left value in here, so I can just say left value is whatever is there in east, right value is whatever is there in west. I just take it off, and here the lexic scheme I have to apply for each of the variables. For each of the variables I need to calculate the flux, and I need to multiply it by dy, and I need to add it to the flux or subtract it from the flux. Okay, so all these things will go inside the variable. Look, so okay, so the flux is 0.5 into the variable. Okay, here I'll say double, let me call it wave speed, that's going to be equal to, okay, now I'll have wave speed left and wave speed right. So wave speed left is going to be equal to left value left value is 0. Okay, I'm just thinking how should I do this. So let me define required variables first, and then I'll calculate the wave speed. So I'll say double UL is equal to left value 1 divided by, in fact I'll say HL double HL is equal to left value 0. This is fine, UL, and double VL is equal to left value 2 divided by HL. So now I have all the required left values. Oh, I also need the CL, that should be equal to square root of so let me say double gravity is equal to 9.81. So gravity multiplied by HL, that will be my CL. Now same thing will also follow for the right hand side values. So HR is going to be the right value, R is going to be the right value divided by the right value, right value. Okay, so HR is right value 0, UR is right value 1 divided by HR, VR is right value 2 divided by HR, and CR is gravity and HR. Okay, and now I can say double say lambda max speed R is equal to, in fact max speed R for, in fact I do not need this here, is equal to UR plus CR, and sorry, this is going to be the absolute value of, so absolute value of UR, and this should be capital. Okay, so we have this thing in place, so looks fine. Similarly, we will have max speed L. So max speed L is going to be UL plus CL. Okay, and looks like for the vertical edges, for the vertical faces, we have calculated the speed, and that is what is going to go in right here, not here. In fact, I do not need to calculate the absolute value now, just going to go in there. Oops, sorry, I now have to calculate the max speed which is going to be equal to the max speed left and max speed R. So I have the max speed Now I can just copy this and I can put it in right over here, and I can put the I calculated the flux, and here this actually should be the flux, so we need to calculate the flux. So okay, let me define a function here called f, that is the so let me make it private, double array called f, and what is it going to do is it's going to take a double u, array of u, and it's going to return an array. Similarly, I will also need g, which will again take u and return g. So this is going to be, can I directly do it and return? Okay, let's not do that. Okay, so what will we need? We will need gravity 39.81, then we will need u, which is equal to, let us find h first, h which is equal to u0, then we will need u, which is equal to u1 divided by h, then we will need v, which is equal to u2 divided by h, then we will need that's it, I guess. And I can return a new array, and I'll put all the values right over here. Okay, so what are these values going to be? So it's going to be hu, maybe I can try to again. So it's going to be h times u. The second one is going to be h times u squared plus half g multiplied by h squared. Okay, so we have h u squared plus half g times h squared, this is gravity, and the last is going to be h multiplied by u multiplied by v. So we have f defined. Now similarly we have to define g as well, so let us do the same thing. This is not going to change, however what I return is going to change. So it's going to be a double array so what is this going to be? So we will have hv, then huv, then we will have h into v squared, h into v squared plus half times gravity multiplied by h squared. Okay, So things look fine. So G is defined, F is defined. Now we can go back. Oh. Okay, so where were we? So I was right over here. So we have now this 0.5 into, now we need the flux here. So we'll have, okay, now let me calculate FL, which will be equal to, so FL is going to be equal to F of left value, so that's going to be FL. What's wrong? Oh, actually, this can be static and this can be static. Okay, so FL is done. Similarly, we'll have FR as well, which will be equal to F of right value, and then we can do this. So we'll have FL of variable plus FR of variable 0.5 minus 0.5 times max speed times right value, right value variable, left value variable, and that should be good enough. And then we have flux being calculated. Flux, whatever flux we get, we'll multiply it by dy and then sell total flux for the variable is going to be added and subtracted. So we are done with the flux calculations for shallow water equations here, and the same thing will happen in this case as well. So in fact, I think I can copy paste a lot of these things. So instead of east to west, we'll have, okay, let's not take that risk. Let me do it all over again. So left value, right value. Left value is going to be the north value. Right value is going to be the, oh yeah, I can actually copy because everything in between is not going to change. So I can say gravity, calculate the max speed, and everything will remain almost the same. Yeah, I have to make some changes though. So I should comment this line, uncomment this line, and I should comment this line and uncomment this line, and gravity is this, H is this, VL is this is going to be VL plus CL, CR, this is going to be VR plus CR, and max speed is max speed left, max speed right. Looks okay. And the flux is going to be same as that. So here it will be 0.5 times. Yeah, this has to now go inside a for loop. Number of variables, and I don't know, I will put this on top. This thing Yes. The flux is being calculated as 0.5 times, not left value, but before that let me calculate FL is equal, not FL, GL is equal to G of left value double GR is equal to G of right value, and so for each of the variables 0.5 times, so we'll have GL variable, GR variable. So we can actually see the one-to-one relation here, GL plus GR divided by 2. So GL plus GR divided by 2 minus 0.5 times, we don't need this anymore, this is going to be max speed times right value, the variable, minus left value of the variable. Cell I horizontal flux, total flux for the variable is going to be that value. Okay, I think the flux calculations are done for the shallow water equation, and now let's look at the time integration part. I don't think this is going to be very difficult because we have to just update the cells. Okay, let me first of all look here. So the next thing is calculation of flux. Now flux is done. The next thing is update. Okay, next one is time integration. Okay, so area is this, number of RK steps. It's switching on number of RK steps. This has to be updated for each of the variables. We can just cut it from here and put it right over here. This is going to be capital U, RK step plus 1 at the variable is going to be equal to capital U RK step of that particular variable plus dt divided by area multiplied by cell total flux of that particular variable. So this is done. Here again oh yeah, this is here it will be, well actually I can put it in here or I can also put it out there. So then it is case 0. I think I can put it here. For variable is equal to 0, number of variables, cut it and paste it. This is going to be capital U, RK step variable, this is going to be capital U, RK step variable, and this is going to be variable. Okay, and well the thing is that I do not want to put this for loop again and again and again. So what I'm going to do is I'm going to put it right over here and I'm going to close that for loop right over here. So this cases will be evaluated thrice. That should be fine, I guess. So we will have a capital U here and we will have variable here, we will have a capital U here we'll have variable here, we'll have capital U here, we'll have variable here, and there is flux. Okay, so this looks fine. And now the final case. This is a 3-case scenario. So I think I can just before the switch, I'll the variables. So this is done. Now I'll go through all the variables. Okay, so looks like the time integration part is also done. Okay, and something is missing. What's missing? I missed. Right, this thing. Now let's look at the next step, which is variable copier. In here again the same thing, we have to copy each of the variable. Alright, and finally the error calculation. In fact, I'm not going to implement it now. I'm going to just comment it out and leave it as it is. This I have already fixed. This is done, and let's run and see what we get. So let me change the stopping time. I'll change this to say 80 by 80 or so, and I'll change stopping time to say 0.1 seconds, and let's just say this is fine. Okay, so let's this will not work. So this has to be first order because we have not implemented the others. And let me run this code and see what happens. Run anyway. Okay, so it was able to reach this time, and let us check the output. And let me take this and I'll run this, and it's plotting the solution. And oh wow, something is happening. That's awesome. Let's see what happens when the time progresses even further. Stopping time is 0.2. Run this, run anyways. Now there is one thing that we need to do, that is application of the boundary condition, and I had purposefully kept it at the end. So we can see that the peak is going down and it is spreading out. That is 0, it's slowly growing. We can see some kind of effects happening here. So I'll make it 0.4. Let its periodicity play some role, which is going to be, I don't know, might cause some problems, I guess. Okay. Okay, let me continue with the solution and see what happens. So let me go up to say 5 seconds. I don't know, something done is 5 seconds. Let's see what effects can we see. So this is going to take a long time to create all the solutions, so let's just wait and watch. First of all, it is getting diffused, and then you see some kind of an effect here. Then since it's periodic, it is as if there are infinite amount of such problems being solved in every grid. So goes, bounces, it comes back. Actually that makes sense, I guess. Then again they all come together, form a wave, they come, go, bounce back, then they come together, there's a valley over there. It would be cool to look at it as a 3-dimensional wave like the one which is shown right over here. Okay, so now we have a code capable of solving the shallow water system of equations, which are the shallow water equations, and now we have also had a plotting code which was a 2-dimensional contour plot, but it does not look that good. I mean, it would be much better to have a surface plot. So I have written this small code which basically I have modified the previous existing code, which just plots x, y and the height as a surface, and yeah, that's it. It also draws a box displaying the domain. So when I run this code and it produces this particular output. So here this is the starting point, and then as we progress, the water collapses down due to gravity, and it produces nice artifacts which look very natural actually. So if I run or display this very fast, then it looks pretty good. It looks as if there is some collapsing of a column, and then there are these waves which move in the domain. So it looks pretty natural actually. Okay, and I have created this small animation using the pictures generated by the plotting program, and this is what we have. Okay, so that is what we have for now. Also, this error calculation and this red thing is annoying, so let us get rid of that. Not because I'm going to use it, but it's just annoying. So I'll make that capital U, and let us say that we are just taking a difference of the height function. Anyways, I'm not going to use it just to get rid of that error. And so okay, we don't have any error anymore, so whenever I run this code, it won't say that there are errors in the code, and whatever the earlier message which it was showing, that will not be shown anymore. Okay. to continue. Okay, yeah. There are a couple of things that still have to be done in this code for completion. The first thing is the variable reconstruction. Now we are only reconstructing the first order using the first order method, which is not that accurate. We may want to modify the code to also work with higher order schemes as well, higher order reconstruction, that is. And it's pretty simple actually. Just we need to make these capital U's and add these extra the second index for variable. We have to do it everywhere, and that's it. We will have a higher order scheme. So I'm not going to spend a lot of time, at least not. I'll not be capturing a video of it, because I know it is going to be really very boring, me just changing these variables here U and adding the variable. That's it. Second index for variable. So I'm not going to do that. And the second thing which is pending is the application of boundary conditions, and that's a very important thing, and I'm going to spend a little bit of time explaining that. So I think I'll insert one more page to explain the boundary conditions. So there are two ways in which we can apply boundary condition, at least two ways in which I know of application of boundary condition. One is the calculation of flux directly. So directly calculate the flux, and so calculate the flux for the boundaries. And the second method is to set up the ghost cells such that the boundary conditions are satisfied. These are the two ways in which we can apply boundary conditions. So we will be using the second method, but I'll briefly explain this method as well. So how do we directly apply the boundary conditions is, let us say we have a domain. So in this domain we need to apply the boundary conditions at these four boundaries. And because we know the boundary conditions, we can actually calculate the flux, exact flux which is crossing these boundaries. So if you look at the shallow water equations, for example, then in case of shallow water equations, we have these three, that is HU square plus half GH square, and HUV as the flux vector for F, and similarly we have a flux vector for G. So at the boundaries, say for example for the vertical walls, if you assume this to be walls, then there is no the perpendicular component of velocity is 0, and in case of inviscid flow the tangential component can exist, but the normal component of velocity is 0. So in such a case it is equivalent to saying that U is equal to 0. So if you substitute U is equal to 0 in this flux, then you will see that this first term will be 0, the term HU square will be 0, and this particular term HUV will also be 0. The only term which will remain in the flux vector is half GH squared. So for this wall and for this wall, so here the flux vector is going to be 0, half GH squared, I think, half GH squared, and 0. So this will be the same vector for this wall as well. For the horizontal walls, the y component is equal to 1, that is ny is equal to 1 and x is equal to 0. So only the g vector is important there. So v, in this particular case the normal component is 0, so v is 0, and therefore this is going to become equal to 0, this is going to be equal to 0, this is going to be equal to 0, and we will be left out with half g eta square as the third component. So let me write f here and f here. So g is equal to 0, 0 and half gh squared, and similarly here g will be equal to 0, 0 and half gh squared. So this is one way of applying the boundary conditions directly. So whenever we calculate the flux for these edges of the boundaries, we directly substitute this as the flux vector. So this is pretty straightforward. The only problem which may arise is how to calculate this h. So one of the ways that you can follow is you can calculate the calculate height at the boundaries to be the average of the left and the right cell value. The method which we are going to follow is by using the ghost cells, and we will be setting up the ghost cells in such a way that the flux automatically becomes equivalent to the boundary condition which we need to imply. So let us learn about it in a little bit detail. The reason why I am doing this is because well, we already have the mechanism set up for ghost cells, so we can use it. So let us consider that this is the left boundary. So I'll only derive everything for the left boundary, but it is applicable to the rest as well. So let us consider that these are the internal cells, and let us consider we have two ghost cells. It does not matter, we can have more ghost cells as well, but for understanding purposes let us consider two ghost cells, and there are some internal cells. And let me call this particular cell as I plus 1, I plus 2, and this is going to be I minus 1 and I minus 2. Now in case of the inviscid wall, what we want to say is that the height is not changing at the boundary. In other words, the derivative of height with respect to x is equal to 0. The second thing that we want to imply is the velocity. So del u by del, not del u. The velocity is equal to 0. So u is equal to 0 for the horizontal wall. For the vertical wall. For the horizontal wall, however, v is going to be equal to 0. So for vertical wall, u is 0. And the third boundary condition which we want to imply is del v by del x is equal to 0. In other words, the normal component is 0. The tangential component is not changing across the wall. So it's the slip boundary condition that we are trying to apply. So these are the three conditions which we would like to apply. Okay, so how do we apply these boundary conditions? So to understand that, let us draw some plots. So let us consider h versus x. So let us say that we know the values, the centroidal values for h inside the domain, and we need to set up the ghost cell values. So to imply del h by del x equal to 0, so we just say that these two values are same and these two values are same. These two values are same. So this value is same as this value, this value is same as this value. When we look at the mesh, it means that so this is hi, this is hi plus 1, this is hi minus 1, and this is hi minus 2. So hi minus 2 is equal to hi plus 1, and hi minus 1 is equal to hi. So if you try to fit a curve through these points, so these points, what you will see is that the derivative at the interface, derivative at the boundary becomes equal to 0. That's what the boundary condition implies. The second thing what we want to imply is u is equal to 0. So u is equal to 0, what does it mean and how do we apply that boundary condition is? So let us say, I should draw this horizontally. So let us say this is u, and say this value is known and this value is known. So to make the value of u equal to 0, that is the function to pass through this point, we need the ghost cells to have this kind of a character, such that when we draw a line passing through all these points, it will kind of pass through the origin. So in other words, ui and ui plus 1 are known, and ui minus 1 and ui minus 2 have to be calculated. So we can say, to imply this boundary condition, ui minus 2 is equal to minus of ui plus 1, and ui minus 1 is equal to minus of ui. So now this is what we need to imply. So in our conservative vector, the first one is h, the second one is hu, and the third one is h times v. So what we are going to do is, we are going to say that we know the first value in the conservative vector, so we can easily apply this, the first boundary condition, that is del h by del x is equal to 0. To apply the second boundary condition, we will just reverse the signs of this. So in other words, we are going to say h times ui minus 2 is equal to minus of h times ui plus 1, and h of ui minus 1 is equal to minus of ui times h. So this is actually what we are going to, this is actually how we are going to apply the second boundary condition, that is on u. Now the third boundary condition is a little bit tricky, so let us try to understand that. So the third boundary condition what we need to apply is del v by del x is equal to 0, and the vector which we have, that is the conservative vector that we have, is h, hu and hv for all the internal points. So let us consider this is equal to u3, that is the third value in this vector. This is velocity u, and this is third component of vector, so not the same. So if we say, what we want to imply is del v by del x is equal to 0, but we don't have v directly available, but what we can say is del vh by h by del x is equal to 0 based on what we want to imply. So in other words, del u3 by h by del x is equal to 0, and what does this imply is, if you take the derivative with respect to x here, then you will get, you will have h times del u3 by del x minus u3 times del h by del x divided by h squared is equal to 0. But since the right hand side is 0, we can get rid of this. this is equal to 0. Also we know that this is equal to 0, and therefore we can say that del u3 by del x is equal to 0. So in other words, to apply the boundary condition del v by del x is equal to 0 is equivalent to saying that del u3 by del x is equal to 0. So this is what we are going to apply for v. So it will be very similar to the way we are doing for h. Okay, so this is how we are going to apply the boundary conditions. To summarize very quickly, if this is our mesh, say 2 ghost cells and 2 internal cells, so this is going to be all the internal cells, and this is our boundary. In such a case, when we want to apply that the derivative is 0, then this value should be equal to this value should be equal to this value, and when we want to apply that the value is equal to 0, then this value is negative of this value and this value is negative of this value. So that is how we are going to apply the boundary conditions in our case. I hope that was not very confusing. So this particular thing wherein we are going to say the values are this is same as this, and this is same as this, and this is same as this, will be applied for the first one. So that is del h by del x equal to 0, or in other words, this will be applied for the first element of the array, that is h, and it will be applied for the third element of the array, that is h times p, and these two, that is the negative sign one, will be applied for the second one, that is hu. I hope that is clear. So I'm not so sure. If there are any doubts, please let me know in the comments, and I'll try to help you out. Maybe I'll provide some more details, because boundary conditions are always very tricky, and if you do not apply right boundary conditions, your solutions are going to be wrong. So boundary condition is the only way in which we tell the numerical solver how the physics is interacting with your solver. So even if your partial differential equations remain same irrespective of the kind of problem you're solving, the only way in which the problem changes from one problem to another is either the initial conditions or the boundary conditions. So application of boundary conditions is very important to be done correctly. So let us now update our ghost cells to apply the boundary conditions. Okay, now I have to think a little bit because I have not thought about it. How am I going to apply the boundary conditions? So here these are periodic boundary conditions. So variable 0, variable 1 and variable 2. So this is for the left and the right side of the domain. So I don't know how I'm going to do this. So let me say int variable equal to 0, and in such a case I want to do something with the two walls, left wall and the right wall. Then variable is equal to 0. Well, I'll get rid of this as of now, not required anymore. So similarly I'll have variable equal to 1 and we are equal to 2. So these two need to be changed. So let us do for variable 0, that is for h. We know that del h by del x should be equal to 0. So okay, so these are the ghost cells So we are going to have cell ghost cell 0 so ghost cell is equal to 0 and ghost cell is equal to 1, ghost cell is equal to 2. For each of the ghost cells we need to go in the reverse direction, so it will be number of ghost cells plus so it's going to be number of ghost cells plus 2 times number of ghost cells minus the ghost cells. So the first internal cell, when ghost cell is equal to 0, I'm going to go to the okay, let me just rethink this. So when the ghost cell, one sec, let me look at it. When the ghost cell is 0, so I'm taking the leftmost cell. So this cell should be equal to this cell. So that is equal to, let the number is 0, 1, 2, 3. So that should be equal to 3. So if I do 2 times ghost cell, number of ghost cells, that is minus, so okay, that should be 2 times number of ghost cells minus 0 minus 1. So then this cell should be equal to this cell. So again 2 times number of ghost cells minus 1, that will give me 2 times number of ghost cells will be 4 in this case, minus 1 will give me 3 and minus 1 will give me 2. Yeah, that looks okay. So it should be 2 times number of ghost cells minus 1. So 2 times number of ghost cells minus 1. So that looks fine. Okay, and for the right hand side, number of X cells plus the number of ghost cells. So that is this one plus ghost cell. So okay, that's going to be equal to something times this. So I'll have number of X cells. So this will be number of X cells plus number of ghost cells. Number of ghost cells minus ghost cells minus 1. So number of X cells plus number of ghost cells will take me to just the right hand side of the domain, and minus 1 will bring me back. Okay, I'm just thinking in my head, so let me just draw this. So on the right hand side, so this wall, let us consider this. So number of cells plus the number of ghost cells, when I do, I will be pointing to this particular cell, and what I should do is that cell should be equal to this cell and this cell should be equal to this cell. So what I can do is so this cell here is going to be equal to So this I can name as, this is when the ghost cell number is equal to 0. This is when the ghost cell number index is equal to 1. So when ghost cell number is equal to 0, I should be pointing to this. So that is going to be equal to number of X cells plus the number of ghost cells. That will take me here, minus 1 minus G. So when G is equal to 0, I'll be here. And when G is equal to 1, minus 1 minus 1. So yeah, that will take me to this point. That's correct. So looks like it's fine. Number of ghost cells minus number of ghost cells, and it's fine. Okay, so that looks fine. So now this is for variable equal to 0. Now I can just copy this and paste it here. Now for variable 1, that is h times u. So we want h times u for the left and the right face to be equal to 0. So we just have to flip the signs. So I can just flip the sign here, and I can flip the sign here, and also, okay, variable, it's automatically taking the variable, and also the same thing is going to go in here as well. Okay, so when variable is equal to 2, these are going to be the same. We don't have to flip the sign. So now the same thing has to be done here as well. So when variable is equal to 0, let me copy and paste it, and I can get rid of this. I'm going to do this in a much more standard way later on, when we look at more generalized framework. That would be after we look into the details of Riemann solver and all, but as of now we are going to implement it just for the shallow water equations, just to make sure that we have some base code over which we can work upon as we go ahead with the detailed tutorial on Riemann solvers and flux calculations and all the stuff, a lot of stuff actually. How do we deal with system of partial differential equations? So those are going to be the upcoming videos, but as of now, let's deal with the problem at hand. So here I is going to be same. So this value, so J has to change here, and will change very identical to what we have done here. So it's going to be 2 times number of ghost cells. So instead of this, we will have 2 times number of ghost cells, 2 times number of ghost cells minus ghost cell minus 1. This is for H, and also this is going to be equal to number of X cell, number of Y cells, number of Y cells plus the number of ghost cells minus ghost cell minus 1. That's going to be the J coordinate of J index of it. Okay, and that's it for variable 0. Let me also apply it for variable 1 and variable 2 as well. So variable 1 and variable 2. So for horizontal edges, this is going to be same. This one is going to flip signs. Okay, seems like the boundary conditions are being applied properly. Now we should be able to solve much better problems which are non-symmetrical. Earlier we were applying the periodic boundary conditions, which were okay because they were kind of they turn out to be reflective boundary conditions when the initial conditions are symmetric. But for non-symmetric initial conditions, we will not get the right solutions. So this is a much better approach as far as our problem is concerned. These are the reflecting walls now that we have applied. So let's see if I have not done any mistake, then they should work fine. So let me reduce the time to say 1 second and let me run the code. Let's see what results we get. I think before running the code I should have cleared it off, so that is what I'm going to do now. So Control A, Shift delete, and I will run the code all over again. And once we have the result, I will run this code and see whether we are getting correct results or not. Seems to be collapsing fine, but now okay, looks like the wall boundary condition is working fine. But yep, before we realize whether there is any mistake or not, or to check whether there is any mistake or not, let us use a non-symmetric initial condition. So let me use a dam break kind of a problem and check whether the results match the ones which we can expect from a dam break problem. So let's change the initial conditions now. So instead of saying this, let me change this to say something like if x is smaller than say minus 0.5. If x is smaller than minus 0.5, then make it equal to 1, otherwise make it equal to 0. So that will be like the left side of the domain. Small portion is made equal to 1. I'll make this say 2, and otherwise I'll make it equal to 1. So let's see what results we get out of this. So it does not blow up or anything, and it's producing a lot more files. That has produced 70 files now. Maybe the time step is small. Yeah, the time step will be small because the height is more, so eigenvalues are smaller. So sorry, eigenvalues are larger, therefore the time steps are smaller. So let's see what we get. Oh, I see. I have restricted, so I should basically write this. I have restricted the z from minus this, so I should change it to 2. And now I should run this. This is the starting condition. So when it reaches the right wall, okay, this is good. It should raise height and it should come back and it should hit the right inside wall. Oh, I think it's working fine. Looks like the wall boundary conditions, the reflecting boundary conditions have been applied properly. So that's a very good news. Now I'm going to do one more thing. I'm going to change the, so this is the final solution. So if I run this, then it looks something like this. Wow. So looks like the boundary conditions are okay. Now I'm going to do another thing also. I'm going to make this Y, just to make sure that the other side boundary conditions are also applied properly. So now again those files should be overwritten. I'll just delete this file so that when it gets created, I'll be sure that it has reached at least that point. Okay, at least it has created those many same number of files. And now we will run our plotting code, and the plotting code should now produce the same results but in the other direction. And looks like it is working as expected. Okay, let it finish. Okay, so looks like the boundary conditions have been applied properly as expected. The last thing what I would like to do is I would like to apply I would like to just put the dam at one particular corner and see what happens. So let us say if x is less than 0.5 and y is less than 0.5, then it's equal to 2, else it's equal to 1. So let us see what happens with this particular case. Also, let me make it 1 and like say, okay, let us see the results here. So well, looks fine. Looks like the dam break problem is working fine. And okay, let me make this 2. So one corner of the dam is being, the dam is like, not dam actually, water is being located at one corner, and at time 0 we are allowing it to collapse. So if I plot this now, okay, wait a sec, I will delete the old files. I don't know how many files are created now, so delete, and I will rerun this code. Oh, what did I do? I made a mistake here. I wanted it to be minus 0.5 so that it's put at one corner. So it will stop after 1 second, and let me plot these results now. And what we see should be very interesting, I suppose. Cool. We're getting some nice results. So the dam is now placed like this. I think I should increase the height of these walls, or actually I'll totally get rid of these walls, or maybe I can increase the height of those walls. So what is the height of those walls going to be? So it's going to be 2.0, sorry, it's going to be 2.0 and 2.0. Okay, I'm going to replot this, so I'll include that. 2.0 and 2.0. went low. So now it looks something reasonable. Actually, I should have put the dam on the other side so that we can see it sloshing towards this side. Anyways, doesn't matter. So we can see the dam, the water column collapsing and the wave kind of traveling through the medium, and because of the walls it's unable to go further. It gets reflected and we have these nice patterns being generated. Oh, this is nice. So this looks interesting. Let me put the dam on the other side of this. That will be like actually this is the first time that I'm writing a code for shallow water equations. So, I'm surprised that it worked out really good. Actually, I have written code for Euler equations, Navier-Stokes equations, and compressible and incompressible flow and all, but this is the first time that I'm writing code for shallow water equations. So I just wanted to try it out. I was very confident that I'll be able to do it, but I was not expecting that there'll be no error at all. I mean, it's really surprising. I was thinking at least I'll make some mistakes and then I'll have to rectify it. So what am I going to do now is I'm going to allow this simulation to run for quite a while. So let me make this simulation run for 10 seconds and let us see how the water column behaves. It will take a lot of time to plot, so I think I will pause the video now, and after the plots are done I'll also do some other initialization conditions. I mean, I will initialize this solution with different kind of functions, and then I'll put it as a video towards the end of this video. So I think this is the end of this video as far as the coding is concerned. The next video is going to be, in fact I'll start with very basics of system of partial differential equations and how do we solve it, and I'll start with very basics like a system of equations, Navier-Stokes equations, Euler equations, how do we derive different kind of equations from the Navier-Stokes equations, and then I'll go to Riemann solvers. What do they mean? Why do we need those eigenvalues, eigenvectors? How do we decouple the system of equations, and all that stuff, all the complex stuff. So I'll be dealing with also, I'll again take up the higher order reconstructions, but now for system of equations, and well, I'll be covering a lot of stuff. So I'll see you in the next video, and thanks for watching. Leave any comments in the comment section. If you have any doubts, please feel free to ask, and I normally reply as soon as I can. So thanks for watching again, and I'll see you next time. Until then, bye bye.